In the beginning there is silence. A vast ocean stretches beyond imagination, motionless, without horizon. No wind disturbs its surface. No ripple moves across its skin. Only stillness. Then, out of that stillness, a wave. Delicate, fragile, ephemeral. It rises, trembling with possibility, then falls, dissolving back into silence. Another follows, then another. An endless sea of hidden undulations, unseen yet ceaseless. Each one weaving the foundation of existence. These are not waves of water, nor of sound, nor even of light. They are quantum waves, probability itself, oscillating at the roots of reality. Every particle, every atom, every star and galaxy is born from their restless rhythm. Matter and energy are not solid, but ghostly harmonies, arising from invisible patterns in a cosmic sea. The universe is written in these waves. They guide the dance of electrons around nuclei, the glow of stars, the chemistry of life, the collapse of galaxies into black holes. Without them, there would be no shape, no form, no being. And yet what happens when the last wave fades? When every particle collapses into silence, when every fluctuation stills, does reality dissolve into nothingness? Or is the wave only a shadow, concealing a deeper order waiting to emerge? If quantum waves vanish, does time itself unravel? Does space collapse into emptiness? Or does the end of the wave mark not a death, but a transformation beyond comprehension? The last quantum wave is not only a scientific riddle, but a philosophical abyss. To approach it is to ask, what remains when the music of existence itself goes silent? The story of the quantum wave begins not with silence, but with firelight. At the dawn of the 20th century, physics stood upon what seemed to be firm ground. Newton's laws still guided the planets. Maxwell's equations explained light, and thermodynamics governed heat and motion. The universe appeared ordered, calculable, and eternal. But in the shadows of the laboratory, a quiet rebellion was beginning, whispered, not by philosophers, but by experiments. In 1900, Max Planck confronted a paradox. Heated metal, glowing from red to white, radiated energy in ways classical physics could not explain. The math predicted catastrophe in infinite blaze of ultraviolet light, something nature never revealed. To resolve the contradiction, Planck made what he thought was a desperate assumption. Energy, he proposed, was not continuous, but came in tiny, indivisible packets quanta. A radical fracture had opened in the classical world. The smooth became granular. The infinite became discrete. Planck's quantum hypothesis was born, though he himself doubted its permanence. 5 years later, Albert Einstein took the leap further. The photoelectric effect light, knocking electrons free from metal-made sense. Only if light itself came in quanta, later called photons. This was not merely a calculation, it was a revelation. Light, the most continuous of waves, carried a hidden duality. It was both particle and wave, both localized and extended. The universe had begun to whisper its strangeness. Soon, Niels Bohr applied these ideas to the atom. Why did electrons not spiral into the nucleus, collapsing matter into nothingness? Bohr's answer was astonishing. Electrons could occupy only discrete orbits, their motion governed not by classical mechanics, but by quantum leaps. Atoms, it seemed, pulsed to a hidden rhythm, sustained by rules that defied common sense. In 1924, Louis de Broglie offered an audacious vision. If light could behave as both wave and particle, then matter might as well. Electrons, protons, even larger particles could be described not as points in space, but as waves of probability. Matter itself was not fixed, but undulating. 2 years later, Erwin Schrödinger transformed this vision into mathematics. His wave equation described particles as ripples in abstract probability fields. Reality, at its most intimate scale, was no longer a solid architecture of particles, but a music of invisible waves. An electron around a nucleus was not a point, whirling like a planet, but a standing wave smeared across space, everywhere and nowhere until measured. Then came Werner Heisenberg, who revealed the unsettling price of this new picture. His uncertainty principle declared that no particles, position, and momentum could be known with perfect precision. The more one was defined, the more the other dissolved into haze. The quantum wave was not a lack of knowledge, but a fundamental truth. The universe itself resisted exactness. Nature was probabilistic at its roots. Experiments soon confirmed what equations foretold. The double-slit experiment, conducted with single electrons, revealed interference patterns, ripples of probability when no one was watching. But when detectors measured which slit the electron passed through, the wave collapsed into a particle. Observation itself seemed to alter reality, forcing the wave to choose. Here, in these strange laboratories of the early 20th century, humanity encountered the foundation of existence in a new light. The bedrock was not rock at all, but wave. The universe was woven not from certainties, but from probabilities. Every atom of our bodies, every photon of starlight, every chemical bond of life was born of quantum waves. Yet the question lingered: what is a wave of probability? Is it a physical ripple, like water on a pond? Or is it merely information, a mathematical shadow describing potential realities? The pioneers of quantum mechanics disagreed. Bohr spoke of complementarity, that wave and particle were two faces of one reality. Einstein resisted, unsettled by a cosmos that rolled dice. Schrödinger himself recoiled from the implications, crafting his famous thought experiment of the catalive and dead until observed. Still, evidence deepened the mystery. Cloud chambers revealed ghostly tracks of particles emerging only when measured. Superconductors and lasers, technologies of the modern world, proved that quantum waves were not abstractions, but engines of reality. And yet, a haunting question arose in the silence between discoveries. If quantum waves define the fabric of matter, what lies beyond them? If they are the breath of the universe, what happens when the last quantum wave falls still? Even as physicists marveled at their newfound power, they sensed the enigma within. Probability was not substance, but a veil. The wave carried not certainty, but potential. Beyond the mathematics, something vast and unresolved stirred. The discovery of quantum waves was not merely a triumph of science. It was an unveiling, a glimpse into the hidden music of being. Every star, every life, every thought arises from their rhythm. To follow this rhythm is to trace existence itself, and to ask what lies beyond it is to face the ultimate question: what remains when the wave is gone? The discoveries of Planck, Einstein, Bohr, Schrödinger, and Heisenberg did more than rewrite the language of physics. They fractured the very image of reality. For centuries, the universe had been understood as a vast machine, a cosmic clockwork, its gears and levers governed by strict determinism. Newton's laws suggested that if one could know every particle's position and velocity, then the entire future could be calculated with perfect precision. The cosmos was orderly, predictable, complete. But quantum waves struck this vision with a violence unlike any comet or revolution. They revealed that certainty was an illusion. At the smallest scales, nature did not obey the rigidity of classical order. Instead, it pulsed with ambiguity. Particles did not exist in definite places, but in clouds of probability. They did not choose a single trajectory until forced by interaction. This was the first great shock. The universe was not deterministic, but probabilistic. An electron could be in multiple locations at once, its wave describing all possibilities. A photon could traverse two paths simultaneously. Entire systems could exist in superposition, occupying states that classical logic would call mutually exclusive. A quantum wave did not declare what is, but what may be. Reality itself seemed suspended between futures, awaiting collapse. The collapse came with measurement and observation, an interaction, an act of entanglement with the wider world. In that instant, the spread of probabilities narrowed into a single outcome. The wave dissolved, and the universe made a choice. But why? What mechanism enforced this collapse? Was it the act of conscious observation, or the inevitable decay of a fragile system exposed to its environment? To this day, the answer remains elusive. For Einstein, this was intolerable. He had helped midwife the quantum revolution, but recoiled from its implications. God does not play dice with the universe, he protested, convinced that quantum mechanics was incomplete. Somewhere, hidden variables must restore order. Yet experiment after experiment proved otherwise. No hidden certainty lurked beneath. The dice were real, and they rolled everywhere. The second shock followed swiftly, and it was more haunting still. When two particles interacted, their quantum waves became linked in a single mathematical description. No matter how far they separated, their states remained intertwined. This was entanglement, a connection that transcended space itself. Measure one particle, and its partner's wave collapsed instantly, even across vast distances. Einstein derided this as spooky action at a distance. But Bell's theorem, and experiments that followed, confirmed it. Entangled particles shared a bond no classical signal could explain. Their probabilities were not separate but unified, as though reality itself ignored the limits of distance. The shock was not only scientific but philosophical. The quantum wave revealed that separateness itself was an illusion. The third shock arose from the question of non-locality. If quantum waves could entangle across light years, what did that mean for causality, for relativity, for the principle that nothing could travel faster than light? The equations held, yet intuition faltered. The universe seemed to honor both relativity and entanglement, but the reconciliation of the two eluded. Understanding this growing unease culminated in the recognition that the wave function itself was not objective reality. It was a tapestry of probabilities, a description of potential futures. But does the wave exist physically, or is it only a tool for human knowledge? If it is real, then the world is woven from shimmering clouds of uncertainty. If it is not, then what are we to make of its collapse? The final shock came with the realization that quantum waves imply a fragile, relational universe. Existence is not fixed in stone, but sculpted through interaction. Reality is not a stage upon which events unfold, but a story written only as it is read. This was a profound rupture in the philosophy of science. For centuries, reality had been assumed to be absolute, independent of observation. Now, it seemed that existence was relational, born in the act of connection. This revelation carried with it a darker implication. If the quantum wave defines existence, then what happens when waves vanish? If probabilities collapse into silence, if entanglement unravels, if the last oscillation fades, does reality itself dissolve? Or is there a deeper stratum beneath, unseen, waiting? For physicists, the shock was not only intellectual, but existential. The quantum wave demanded that the cosmos be understood as fragile, uncertain, alive with possibility, yet haunted by its own impermanence. The machine had become a dream. The solid had become spectral. The eternal had become contingent. The scientific shock of the quantum revolution was not simply that the rules had changed, but that reality itself had shifted beneath our feet. Certainty was gone. In its place, probability ruled. The universe had revealed itself as a wave rising, falling, collapsing, reborn. But beneath that revelation lay a question more haunting than any. If all is wave, what lies beyond the last? The shock of the quantum wave did not silence inquiry. It ignited it. If probability governed the smallest particles, then reality itself demanded new equations, new tools, new visions. Out of this fire was born quantum field theory, a framework where particles were no longer the foundation, but vibrations of deeper fields that filled all of space. Every type of particle, electron, photon, quark, was revealed as a mode of a field, much like a note plucked from a string. These fields did not end at the edges of matter. They extended everywhere, invisible yet present, a universal ocean. To speak of particles was to speak of localized excitations, but beneath them lay waves without end. Here the question grew stranger. Still, if reality is fields, and fields are waves, what then is the vacuum? Classical thought imagined emptiness as nothing. Quantum field theory declared the opposite. The vacuum was alive. It seethed with constant fluctuations, verticals flickering into existence and vanishing in instants. What appeared silent was, at its roots, a storm of hidden waves. This truth was not philosophy. It was measured. The Casimir effect, discovered in 1948, revealed that two uncharged metal plates placed close together experienced a tiny force pulling them inward. Nothing pushed them, nothing visible. Yet the energy of vacuum fluctuations, restricted between the plates, left an imbalance. The plates moved because the vacuum itself was restless. Empty space was not empty. It pulsed with unseen waves. Physicists began to recognize that these fluctuations were not mere curiosities. They shaped everything. They contributed to the mass of particles. They altered the behavior of atoms. They even hinted at the origin of the universe itself. The vacuum was a stage not of stillness, but of infinite motion. But the deeper one studied, the more haunting the question became. Can the waves end? If they define reality, what happens beyond their final oscillation? In the 1970s, black holes became the crucible for this question. Stephen Hawking, extending quantum theory into the curved fabric of space-time, discovered that black holes were not silent voids. They emitted radiation. Hawking, radiation born from quantum fluctuations at their horizons. Pairs of virtual particles appeared near the boundary. One fell in, the other escaped, stealing energy from the black hole. Over vast epochs, even the most massive black hole would evaporate. Here, in the marriage of relativity and quantum theory, lay a terrifying implication. The quantum wave itself governs the fate of stars, galaxies, and space-time. Without fluctuations, Hawking radiation would vanish. Without waves, the laws of thermodynamics falter at the edge of a horizon. Yet black holes revealed another paradox, the information problem. If waves collapsed inside, their patterns seemingly destroyed, what became of the knowledge encoded within them? Did information vanish? If so, the most sacred principle of physics, that information is never lost, would be broken. The enigma deepened. Waves gave rise to information, yet horizons threatened to erase it. Beyond black holes, the quantum wave expanded to embrace the entire cosmos. In the 1980s, cosmologists began speaking of the universe itself as a wave function. Could reality as a whole be described by Schrödinger's equation, a single cosmic wave evolving in timeless probability? This idea reached its most haunting form in the Wheeler-DeWitt equation, a mathematical attempt to unite general relativity with quantum theory. Strangely, it contained no time. The wave function of the universe was timeless, static, suspended. In possibility, time itself might not be fundamental, but emergent, born only when quantum waves interact. If that is true, then what lies beyond the last wave may not simply be silence. It may be the erasure of time itself. Experiments continued to peel back layers. In laboratories, delicate systems of photons and atoms revealed the process by which fragile superpositions collapse when exposed to environments. The transition from quantum to classical was not a mystery of consciousness, but of entanglement with the vastness around. Waves died when they could no longer remain isolated. They dissolved into the larger ocean, but still the question lingered. What of the ultimate end? If all systems decohere, if all waves collapse, is there a final silence? Or does the vacuum, restless with fluctuations, ensure that waves never truly cease? Cosmology turned the question outward. The cosmic microwave background revealed faint imprints of primordial fluctuations stretched across the sky. These quantum waves, amplified by cosmic inflation, seeded galaxies themselves. Every cluster of stars, every spiral of light was born from quantum noise magnified into structure. Without the wave, there would be no cosmos. This realization carried a paradox. If quantum waves birthed everything, can the universe survive beyond them? If they ever stilled, would galaxies dissolve not just into darkness, but into non-being? The investigation deepened into speculation. Could quantum fields decay? If our vacuum is only a false vacuum, perched precariously above a deeper state, then a single fluctuation could trigger collapse. The last wave would not fade gently, but rupture existence in an instant, rewriting the laws of physics as a bubble of true vacuum expanded at the speed of light. And yet, evidence also suggested resilience. Quantum chromodynamics, the theory of strong interactions, revealed that confinement itself arose from waves. The patterns seemed woven so deeply into the structure of matter that their end appeared unimaginable. The search pressed into extremes: supercolliders, probing high energies, telescopes scanning the earliest light, gravitational wave detectors listening to the vibrations of spacetime. Each instrument revealed the same truth. Beneath every observation, the quantum wave was present. Its rhythm defined all that is, but the mystery endured. If waves shape the cosmos, what lies beyond them? Are they eternal, fluctuating without end? Or will there come a silence where probability itself dissolves? This was the deeper investigation, a journey through vacuum, field, horizon, and cosmos. Each discovery drew the same haunting conclusion. Waves are not shadows of particles, they are reality itself. And the question that remains, suspended over every experiment, every equation, is the one no theory can yet resolve: what lies beyond the last quantum wave? The deeper the investigation went, the more fragile the foundations of reality appeared. What had once seemed like the ultimate description of natura, universe of particles and waves, now revealed cracks in its surface. Every experiment, every telescope, every equation whispered the same unsettling truth. The quantum wave is not just a feature of reality. It may be reality itself. But what then if those waves were to vanish? The question grew heavier with every discovery. Quantum mechanics does not merely describe the motion of electrons or photons. It defines the structure of space-time. Quantum fluctuations gave rise to galaxies. Entanglement, some theorists propose, is the very stitching of space itself. According to the conjecture known as E equals EPR, the geometry of space-time may be nothing more than a manifestation of quantum entanglement. Wormholes and particle pairs, bound across distance, may be shadows of the same principle. If this is true, then the cessation of quantum waves is not the end of particles. It is the unraveling of space-time itself. Here the mystery deepens into terror. Imagine a universe where not even geometry survives, where distances and durations evaporate. Without quantum waves, not only matter dissolves, but the very idea of place and moment. The universe would not fall into darkness, but into meaninglessness. This fear echoes through cosmology's most haunting scenarios. In the distant future, entropy marches toward its maximum. Stars exhaust their fuel, galaxies fade, black holes evaporate. The universe drifts toward heat, deather, state of equilibrium, where no gradient remains, to power, structure, or change. But what happens to quantum waves in that silence? Do they persist as restless fluctuations, ensuring that the vacuum never truly stills? Or do they stretch thinner and thinner until probability itself becomes flat, no longer a living ocean, but a frozen plain of timelessness? The paradox grows sharper still. If the vacuum fluctuations end, then even the Casimir effect would vanish. Black holes would fall mute. Thermodynamic law itself would lose its foundation. Physics, as we know it, would not survive. And yet, the alternative may be even stranger. If fluctuations persist without end, then the universe is condemned not to silence, but to an eternity of meaningless noise. Quantum waves would continue forever, seeding possibilities in a cosmos too empty to realize them. A barren eternity filled not with stillness, but with restless, unfulfilled probability. The weight of this dilemma deepens with cosmology's boldest frontiers. Consider the possibility of quantum nothingness, a state beyond fluctuation, beyond wave, beyond probability. It is not emptiness, for even emptiness in quantum theory is alive with activity. It is something harsher, stranger, an absolute silence where no wave rises. Such a realm may lie beyond our mathematics. If reached, it would mean the erasure not only of matter and time, but of the very language we use to imagine reality. The last quantum wave becomes more than a boundary of science. It becomes a philosophical abyss. For if everything, atoms, stars, thought itself is woven of these waves, then their silence is not simply the end of physics, it is the end of meaning. This escalation is not only theoretical, it reverberates. In the puzzles of cosmology itself, the cosmic microwave background, stretched across the sky, contains horizon-scale anomalies, alignments, cold spots, patterns that defy pure chance. Could they be traces of physics deeper than quantum waves, echoes from before time as we know it began? If so, the universe may already carry scars of what lies beyond. The mystery intensifies further with the idea of false vacuum decay. If our vacuum is not the true ground state, then the last quantum wave may not fade gently. It may end in rupture. A single fluctuation could tunnel into a deeper vacuum, expanding as a bubble at nearly the speed of light, rewriting the rules of physics. As it consumes the cosmos, every quantum wave, every field, every law would vanish. Probability itself would be replaced. For those within, it would be instantaneous, end beyond observation. This possibility does not merely threaten existence, it undermines the very hope of permanence. Nothing we build, nothing we know, nothing the universe contains could survive. Beyond the last wave in this scenario lies not silence, but transformation so absolute that no trace remains, and still another escalation arises. In some interpretations, quantum waves do not collapse. They branch. Each possibility is realized in its own universe. The so-called many worlds interpretation suggests that there is no last wave. Reality is an endless fractal of branching outcomes. If true, then the search for the final wave is futile. There will never be silence, only eternal multiplication. Yet even this is not comfort. For branching without end is a kind of prison, a proliferation of possibilities where no closure is ever possible. Eternity not as stillness, but as endless proliferation. The paradox becomes existential. If waves are eternal, we are trapped in infinite possibility without conclusion. If waves die, we are cast into silence without being. Between the two lies only uncertainty. The last quantum wave, then, is more than a scientific enigma. It is a mirror held to existence itself. Beyond it may lie nothing or something stranger than imagination. But either way, the boundaries of physics quiver under the weight of the question. At the frontier of knowledge, where observation falters and equations strain, the question of the last quantum wave becomes not an answer, but a spectrum of possibilities. Here, science does not close its eyes. It dares to speculate, to imagine. Realities that may never be observed yet might hold the key to existence itself. One vision sees eternity. In this picture, the quantum vacuum never falls silent. Quantum vacuum, eternity, a state where fluctuations are immortal. Even as stars fade, galaxies dissolve, and black holes evaporate, the restless whisper of probability continues without end. No matter how empty the cosmos becomes, particles will flicker into being, rise from the void, and vanish again. In this view, the universe never reaches silence. It becomes a ghostly sea of endless noise, a background murmur that no observer may endure long enough to witness. But another theory whispers something darker, false vacuum decay. What we call emptiness may not be the true ground state of reality. It may be precarious, balanced above a deeper well of existence. If so, then one day tomorrow, or trillions of years hence, a quantum fluctuation could tunnel into this truer state. A bubble of new vacuum would appear, expanding at the speed of light. Inside, the laws of physics would be rewritten. Outside, nothing could escape. All quantum waves, all structures, all memory of the former universe would vanish. The last quantum wave, in this scenario, does not fade gently into silence. It is obliterated in an instant, replaced by something so alien that the word existence itself may lose meaning. Others imagine not silence, but exhaustion. The universe expands, carrying galaxies farther apart, stretching wavelengths until even fluctuations lose coherence. This is the heat death of quantum fields. In this vision, fluctuations do not stop, they are pulled beyond recognition, so attenuated that probability itself becomes uniform. There is no noise, no silence, only a flat plane without structure. The last quantum wave is not an event. It is a slow fading, a long twilight where time itself drifts into irrelevance. But there are wilder visions still. Some cosmologists suggest that there is no last wave because there is no single universe. In the multiverse hypothesis, quantum waves branch eternally, spawning new realities at every fluctuation. What appears to be collapse is merely division. Every possibility is realized somewhere. From this perspective, there is no silence, no exhaustion, no collapse. The last quantum wave never comes, for the symphony of existence is infinite, playing in parallel universes without end. Yet even this is not the final word. The search for deeper structure leads to theories beyond waves. Loop quantum gravity suggests that space-time itself is quantized, built not from continuous fields but from discrete units, tiny loops woven into geometry. In such a universe, waves are not eternal. They are emergent, born from deeper mathematics. Beyond the last quantum wave may lie a geometry not of fields, but of networks, atoms, of space and time, indivisible, eternal. If true, then the fading of waves would not be the end, but a return to the bedrock of being. String theory whispers another possibility. If particles are not points, but strings vibrating in higher dimensions, then quantum waves are shadows of a deeper music. The last quantum wave in our universe might not be silence at all. It might be a transition where the symphony continues on other dimensions, unbound by our horizon. What we perceive as an end may be nothing more than a change of key. Some theorists turn to the holographic principle, born from studies of black holes. It suggests that the three-dimensional universe is a projection, information encoded on a two-dimensional surface. If so, then quantum waves may not end. They may persist forever. On the horizon of reality, encoded as pure information, the last quantum wave in the cosmos would not vanish. It would be preserved, inscribed on the boundary of time itself. Silence, in this vision, is impossible. Every fluctuation, every particle, every breath of probability is written into eternity, and yet speculation can go further still. Some physicists dare to imagine that quantum waves are not fundamental at all, but emergent phenomena. They may be patterns rising from something deeper known, mathematics, hidden variables, structures, beyond space and time. In this view, the last quantum wave is not an end but a doorway. Beyond it lies another order of existence, one we cannot yet describe. The silence of the wave may reveal not nothingness, but the true foundation beneath the illusion we call reality. Each of these theories carries weight, and none are proven. The eternal vacuum, the sudden rupture, the endless branching, the quantized geometry, the holographic inscription, each is a possibility, a story written at the edge of science. What unites them is not certainty, but wonder. They remind us that reality, as familiar as it feels, is balanced on a mystery too vast for comprehension. The question remains, what lies beyond the last quantum wave? Eternity, silence, transformation, or something so far outside imagination that that even our words collapse, unable to carry meaning. Science can build models, test predictions, refine equations, but at its heart, this is a philosophical abyss. 2. Ask about the last quantum wave is to ask about the essence of being itself. Are we woven into probability, destined to fade with its final oscillation? Or are we shadows of something deeper, carried by a structure that will never die? No theory yet resolves the enigma. Each offers a glimpse, a possibility, a reflection of what might be. But the truth remains just beyond reach, like the final ripple on an infinite sea. Speculation, no matter how bold, cannot stand alone. To ask what lies beyond the last quantum wave is to demand evidence, measurements, and instruments capable of probing the deepest layers of reality. Yet how does one measure probability itself, or the silence that might follow its end? Science answers not with finality, but with tools machines of extraordinary precision, designed to listen to the faintest whispers of existence. The search begins with the most colossal instruments ever built by humanity, particle accelerators. At facilities like CERN's Large Hadron Collider, protons are hurled together at near-light speeds, recreating the conditions of the early universe. Here, quantum waves collide, interfere, and collapse, revealing the particles that compose reality. The Higgs boson, discovered in 2012, was one such revelation, a particle born of quantum fields, confirming that even mass itself is woven from waves. Yet physicists suspect deeper structures remain hidden. Supersymmetry, extra dimensions, unknown. Particles, if they exist, accelerators may yet uncover them. Each collision is a question asked of nature. Do the waves we see rest upon something deeper? But not all tools are machines of steel and magnetism. Some are experiments of exquisite subtlety, crafted to detect the invisible life of the vacuum. The Casimir effect, where two plates brought close together feel a mysterious attraction, demonstrates that empty space is alive with quantum fluctuations. Laboratories now measure this force with increasing precision, hunting for deviations that might reveal hidden layers of physics. If the vacuum is destined for silence, its final whispers may already be detectable here, in experiments smaller than the width of a human hair. Still, the most profound testing ground may lie in the cosmos itself. The universe is a natural laboratory, its vastness offering scales no human machine can reproduce. Satellites like Planck and ground-based telescopes, such as the Atacama Cosmology Telescope, have mapped the cosmic microwave background, the oldest light in existence. Imprinted in its patterns are the fingerprints of quantum waves magnified into galaxies. Subtle anisotropies, temperature variations as small as 1 part in 100,000, reveal the seeds of cosmic structure. By studying these patterns, scientists glimpse not only the early universe, but the quantum foundations that shaped it. Future missions will sharpen this vision. The Light-Bayard satellite, set to launch in the coming decade, aims to measure the polarization of the cosmic microwave background with unprecedented precision. Its goal is nothing less than to detect the echo of primordial gravitational wave ripples in space-time itself, born from the quantum fluctuations of the infant universe. If found, these signals would confirm that reality's grandest structures were sculpted by its smallest, that the universe is a cathedral built upon quantum whispers. Other tools turn their gaze not to the ancient past, but to the violent present. Gravitational wave observatories, LIGO, Virgo, KAGR, listen to the trembling of space-time as black holes and neutron stars collide. In these titanic events, quantum mechanics and relativity are forced to meet. Some physicists believe that, in the echoes of these collisions, traces of quantum wave behavior may be inscribed. If horizons carry information, as the holographic principle suggests, then the mergers of black holes may reveal how quantum waves persist or vanish the universe's most extreme boundaries. The frontier extends further still. The Event Horizon Telescope, which captured the first images of black holes, peers into regions where quantum theory and gravity collide most violently. At the edge of a black hole, waves may stretch, tangle, or dissolve into forms unknown. Some hope that future images and models will reveal whether Hawking radiation, itself born of quantum fluctuations, truly exists. If it does, then even the void surrounding black holes is alive with waves. If it does not, the silence beyond may be closer than imagined. Quantum experiments on Earth, too, are pushing limits once thought unreachable. In the realm of quantum optics, particles of light are entangled, split, and recombined, their wave functions tested with precision. Quantum computers, fragile and unfinished, are not merely tools for computation but for exploration. Each qubit, existing in superposition, is a living quantum wave. By manipulating and observing these states, scientists glimpse the mechanics of probability itself. These machines are still primitive, but they offer a window into coherence, collapse, and the elusive frontier where waves may end. On a cosmic scale, astronomers deploy vast surveys to track the acceleration of the universe. Missions like Euclid and the Vera Rubin Observatory will chart billions of galaxies, measuring how dark energy stretches space. By mapping this expansion, physicists hope to understand whether the universe drifts toward eternal fluctuation or collapses into silence. If dark energy is a cosmological constant, the horizon may remain stable, preserving quantum noise forever. If it evolves, if quintessence or phantom energy rules, then the fate of quantum waves may be written into the sky itself. Even supercomputers have joined the search. Vast simulations, combining quantum field theory with cosmology, attempt to model universes as wave functions. These digital experiments recreate the branching of possibilities, the growth of structure, the fading of fluctuations. They are not answers, but rehearsals of what might be, helping scientists imagine what cannot yet be tested. And at the edges of imagination, researchers craft analogues of the universe itself. In laboratories, fluids, light, and even sound are shaped to mimic the behavior of black holes and expanding space. These tabletop universes allow physicists to watch horizons form, to see waves vanish, to test whether Hawking radiation emerges in systems far removed from the cosmos. If such analogues can reveal how quantum waves behave at the edge of existence, they may hint at what lies beyond. Together, these tools form a tapestry of inquiry. Colliders shatter particles to glimpse deeper truths. Telescopes scan the ancient sky for whispers of quantum birth. Gravitational wave detectors listen for echoes of entanglement in colliding stars. Quantum computers test the resilience of fragile superpositions. Every machine, every experiment, is a lantern held up against the abyss, searching for the shape of silence that may come. Yet even with all these instruments, certainty remains elusive. The last quantum wave may lie forever beyond observation, its silence unreachable by any measurement. But science persists, not because it promises closure, but because the act of listening itself is meaning. Each tool built, each signal recorded, is a declaration that the mystery of existence is not ignored. In this pursuit, humanity extends itself into the fabric of reality. The questions asked by accelerators and telescopes are not distant abstractions. They are echoes of the most intimate question of all. What does it mean to exist when existence itself rests upon fragile waves? Return to the ocean, not of water, but of silence. The universe, after its long unfolding, stands poised at the edge of stillness. The stars are gone. The galaxies have dissolved into darkness. Black holes have evaporated, leaving only thin veils. Of radiation, expansion has stretched space beyond recognition. What remains is not noise, but the faintest of whispers, the last quantum waves, flickering at the foundation of reality, and then, perhaps nothing. If these waves fade, if the probability fields collapse into true silence, then existence as we know it ends. Not with a crash of matter, nor a collapse of galaxies, but with the vanishing of the very scaffolding of reality. Beyond, the last wave lies not death in the ordinary sense, but the erasure of being itself. This vision carries a terrible beauty. Human lives are brief, fragile ripples, fleeting against the ocean of time. Yet they are real, carved into the rhythm of quantum waves. Every thought, every heartbeat, every memory is an echo of probability collapsing into form. To exist at all is to be born of a wave. To wonder about its ending is to confront the deepest truth that we, too, are finite. But is the last quantum wave truly an end, or is it transformation? Some philosophers argue that silence is never absolute. If waves are shadows, then their fading only reveals the light beyond. Perhaps what lies beyond the last wave is not absence, but a deeper structure, a foundation where time and space are no longer measures, where existence is no longer bound by probability. To us, it would be unknowable, unimaginable, but perhaps silence is not the end of music. It is its hidden ground, the stillness from which all song emerges. Others reflect on the paradox of meaning in a universe of waves. If everything is contingent, if reality itself rests upon probability, then significance is not given, but created. We do not wait for permanence. We shape it in our brief passage. In this light, the last quantum wave does not erase meaning. It amplifies it. Because existence is fragile, each life, each moment, carries infinite weight. The philosophers of old intuited such truths, though they lacked the language of quanta. Heraclitus spoke of flux, of a world where nothing stands still. The Buddhists imagined impermanence at the heart of all being. Today, quantum physics reframes these intuitions in equations and experiments. The uncertainty principle, superposition, entanglement each reminds us that stability is an illusion, that we live in the midst of probabilities, not certainties. To ask what lies beyond the last quantum wave is to ask whether impermanence itself can end. And there is wonder in this too. If the multiverse is true, if quantum waves branch eternally, then our lives are not singular but infinite. Every choice, every possibility is realized somewhere. The last quantum wave in one universe may be the first in another. In this vision, existence has no edges. It is an endless sea of variations, each wave giving rise to countless others. Silence never comes, only transformation. But even this may be a human projection, a comfort drawn against the abyss. The truth may be stranger still, that silence is absolute, that the last wave does not lead to renewal but to nothingness. And here, philosophy meets its sharpest edge. Can nothingness be conceived? Can a mind built of waves imagine its absence? Perhaps not. Perhaps the final mystery is that we cannot imagine what lies beyond, because imagination itself is a ripple of probability. When the waves end, so too does the capacity to ask. For humanity, this is both terrifying and liberating. Terrifying, because it places a boundary on all knowledge. Liberating, because it reveals that the meaning of life is not deferred to eternity. It is here, in the brief crest of waves that we ride. Our galaxies may vanish, our atoms may dissolve, but the reality that we once were, however fleeting, inscribed in the fabric of the cosmos. One might imagine the universe itself as a memory. Every fluctuation, every collapse of probability, written across time. If the holographic principle holds, then no wave is truly lost. Each is encoded on the horizon, a permanent record inscribed at the edge of existence. Even if silence comes, the memory remains. The cosmos does not forget, and so the question lingers, vast and unspeakable. What lies beyond the last quantum wave? Is it silence, endless and absolute? Is it transformation into a deeper order of reality? Is it branching into infinite multiverse, where the question itself dissolves? Or is it something that cannot be framed, because framing is itself the act of a wave? There is no answer here. Perhaps there never can be. But the act of asking shapes us. To look beyond the last wave is to look beyond ourselves. To confront the abyss of existence and not turn away. The narrative returns to the ocean. Waves rise. Waves fall, each one fleeting yet real. The ocean itself is boundless, mysterious, its depths unseen. Beyond the last ripple lies stillness. But whether that stillness is nothing or everything, we cannot know. What remains is humility. Humanity, a species of fragile beings, born on a small planet around an ordinary star, dares to ask questions that stretch beyond galaxies, beyond time, beyond the fabric of probability itself. That act in itself is extraordinary. The last quantum. Wave may come, silence may fall, but until it does, the universe is alive with oscillations, with rhythms that give rise to matter, to life, to thought. To exist is to be carried by them, a brief crest in a cosmic sea. And when silence arrives, perhaps it will not be an end. Perhaps it will be a return to the stillness that holds all possibility, to the silence that is not absence but potential. For now, the ocean remains restless. The waves continue to rise and fall, and humanity, caught in their rhythm, listens for the distant horizon, waiting for the mystery that lies beyond the last quantum wave.